Hello, welcome back. Today we're going to be taking a look at an application of the gradient. And in this example, we have the temperature in degrees Celsius on the surface of a metal plate. And it's given by this equation. So anywhere on this little plate right here, any XY position, I can find the temperature at that point given by this equation, where X and Y are measured in centimeters. But we want to know in what direction, in this case, in what direction, starting at the point 2, -3, does the temperature increase the most rapidly? And then we want to know what is the rate of this increase. Well, right away we should notice that they're using the phrase temperature increasing the most rapidly. Well, we've been talking about this in our class. This is what we call the gradient. Remember, the gradient is going to give me the direction in which the temperature in this case will increase the most. And we would call that del T in this situation right here. So basically is we're at this point and we want to know what direction should I go in order to make this, in order that I want to increase the temperature the fastest. We want to get hotter quicker. And we're going to use a gradient for this. So we will first calculate the gradient. The gradient is a function of X and Y. And up here, this is just going to become -8x for my change in x. That's my fx. So we get -8x. Remember, this is fx. And here we get -2y. We don't have to worry about the 20 and the 4x here because those are constants in terms of y. So that's our fy right there. And that's our gradient. And let's see here. We are at the point 2, -3. So let's go ahead and plug that in. And whoops, parenthesis there. And if we do this, we get -16. Plug in 3 for y, we get -16, 6. And what this tells us is the direction. This gives me the direction in which the temperature is increasing the most rapidly. Whoops, let me rephrase that, in which the temperature increases the most rapidly. So we're standing at this point 2, -3, and it's telling me to go left 16 and then up 6. Now I can reduce this, because it is a vector, it is a direction vector. I can reduce this to divide everything by 2 and I get -8,3. And it'll still be the same ratio. But we're not going to reduce it, and we'll talk about that, why we don't do that in just a moment. So this says if I go into direction left 16, up 6, it's going to put me in the direction of the fastest increase in temperature. And they drew a little arrow right here for us. And remember, this is our gradient right there. That is the direction that we are going to be heading. The next question says, what is the greatest rate of increase? To get this, we have to use the magnitude, and that's why we're not going to reduce this. If I reduce this, it's going to give me a different value when I want to find the actual rate of increase. To do this, we use the magnitude of our gradient, and this just becomes the magnitude of our -16.6, which is the square root of, what's that, 256 plus 636, and that's going to equal the square root of 292. And you plug it in your calculator, you get about 17.09 degrees Celsius. Now, remember, this right here is a rate of change. This is our slope in the direction that we are heading. So this is not just a temperature, but this is a rate of change. And what this is telling us is at the point 2, -3, if we travel in the direction of our gradient, in the direction of our gradient of del T, the temperature will increases at a rate of 17.09 degrees Celsius per centimeter. So as we're traveling in this direction, the temperature is increasing 17.09 degrees per centimeter we travel in this direction. And that's going to be the greatest rate of change for this. Now, if we reduce this, we would get a different slope. So don't reduce your gradient. Your gradient, even though you can reduce it, we don't want to because it's going to mess up our magnitude if we actually want to find the slope itself. All right, so let's have some fun here. Let's suppose a heat-seeking particle is located at the point 2, -3 on this plate. Now we want to find the path of the particle as it continuously moves in the direction of maximum temperature increase. So what this is asking us to do is to find the path where the temperature is increasing the most. Now, I know some things. One thing I know is, where will the temperature be the greatest? Well, the temperature is the greatest at the origin, at 0, 0. I know that because if I go up to my function, because if I take this 20 minus 4x squared minus y squared, well, if I subtract these, I'm always subtracting. So the biggest it can be, or the biggest this can be is when x and y are both 0. So therefore, the greatest always has to be less than or equal to 20. So I know at the origin, the temperature at the origin is going to be 20. So we're heading towards the origin here. Can you remember? We want to find the path of the particle as it continuously moves in the direction of maximum temperature increase. So if I'm starting at the point 2, -3, we know we're going to wind up at the origin. We just want to know the path that we're going to be taking. Is it going to be a straight path, a curved path, a winding path? We're about to find out. So remember, we are trying to find the path where the temperature is increasing the most. So let's go ahead and come up with an equation for the path. We don't know it, so we're going to do it generically. I'm going to write it as a vector, and this is going to be my change in x and my change in y. Now, because I want to go into the direction of maximum temperature increase, I'm thinking the gradient. Now, what is the gradient? It is a collection of derivatives. So I'm going to take the derivative of my path, or find the rate of change of the path. To get the rate of change of our path, we just take the derivatives. R prime of t will equal, this becomes dx dt, dy dt. What we want this right here to be the greatest increase. That's what we want. We want this to be the greatest increase possible. So in other words, we want this, our rate of change, to equal the gradient. And so we want the gradient to equal this rate of change. So if we can get the gradient equal to the rate of change of the path, we got this. So let's go and set up an equation. So we're going to set up an equation. Write out the gradient. Well, we know what the gradient equals. It's just -8x, -2y, and equal to the rate of change of the path. That's this dx dt, dy dt. And we're just going to solve this. So to solve it, well, it is a vector, so we know like parts are equal. So I know that this -8x equals dx dt, -2y equals dy dt. And this is really kind of hard to solve here. Excuse me. This is kind of challenging to solve here, but I do notice that they both have this dt. So I'm going to solve the d for dt on both of these. Here, dt would become dx over -8x, and over here, dt would be dy over -2y. Since they're both equal to dt now, I know that these are both equal to each other. So I can say dx over -8x equals dy over -2y. The two negatives will cancel. And if I cross multiply, I'm going to multiply both sides by 8 so I don't have to deal with the fraction. we're going to get, if I multiply both sides by 8, I get dx equals 4 over y dy. And you might be thinking, Mr. Warnow, this looks like it's going to be a differential that we did last year in calculus. And it is. We're just going to solve this by using the antiderivative. Oops, I forgot my 1 over x here. There we go. Sorry, I forgot my x. Don't forget your 1 over x right there. There it is. So that makes the complication a little bit more. So when we integrate the antiderivative of 1 over x, we get the natural log of the absolute value of x equals, and this becomes 4 natural log of y plus c1. E both sides, and this just becomes the absolute value of x equals, and in pre-cal we had to do all these little tricky things, but we know what this is going to become. This just becomes c2 y to the 4th, and we can use your power rule to bring that 4 up to the top. So we're going to get two answers here. But when you take the absolute value of x, we get plus or minus c2. That just gets absorbed, so we can just leave that as c2 y to the 4th. And there it is. Solve for c2. And they give us that point, remember, 2, negative 3. If I plug it in, I'm going to get 2 equals c2. Negative 3 to the 4th is 81. c2 is 2 over 81. And we get our equation, x equals 2 over 81 y to the 4th. Notice this is a sideways facing parabola, and this is the path along which always gives the greatest temperature increase. So what this is telling us is, if we stay on this path, if I'm starting at that point, come back up here to the graph, negative 2, 3, this path will always give me the direction that will make sure that the temperature is always increasing the most. And it's a sideways parabola, so it's going to look kind of like this. And we even know the direction. So you can draw little arrows right there to give us some direction. And it's our sideways, and it is a sideways parabola, so again it's going to go like this too, right? And it's going to be symmetric. So this is going to be the point, what's that? 2, 3. All that means, if I'm starting here, it's going to put me in this direction. And there is our answer. Alright, so I hope you enjoyed this video. If you did, smash that like button. See you guys later.